Space stretches in every direction, vast and silent, filled with secrets that defy our understanding. Among its greatest mysteries lies not in the stars above, but in the smallest pieces of reality itself. Down in the quantum world, the rules we know no longer hold. Particles vanish, reappear, and seem to know what others are doing, no matter how far apart they are. Experiments show patterns that bend logic, where time, cause, and observation twist together in ways that make even scientists uneasy. It's a realm that works perfectly in equations, yet feels impossible in thought. Stay with us as we dive into this strange frontier of physics. And if you enjoy exploring mysteries like this one, a quick like and subscribe helps the journey continue. Most of the time, the world around us feels steady and clear. You flip a switch and the light turns on. You drop your keys and they fall. You blink and the room has not changed. Cause leads to effect in a clean line. This picture, built from daily experience, matches classical physics, where objects have positions and speeds at every moment, and the future follows from the present if you know enough details. Newton gave that framework its shape, and later Einstein stretched it to show that space and time link together, and gravity curves that fabric. Even then, events stayed causal and predictable. That confidence weakens when we step down to the quantum scale. There we meet results that do not fit our intuition. A particle can be in a mix of states at once, a situation called superposition. Two particles can share linked properties across great distance, a link called entanglement. The act of measuring can change what is found in a way that cannot be explained, a simple disturbance. Early on, it was easy to suspect that the strangeness came from math tricks or from clumsy experiments. Yet decade after decade, improved tests repeated the same patterns with tighter controls, colder temperatures, faster switches, and better isolation, and the outcomes stayed stubborn. The odd behavior is not a mistake. It is a feature of nature at small scales. This leaves us with puzzles that are not just word games. A paradox here is a clear sign that the basic story we tell ourselves about reality is missing pieces. The delayed choice experiments suggest that choices made during a measurement can line up with earlier parts of the setup, as if the present leans on the past. The details do not mean messages travel backward in time, but they do stress our usual picture of a fixed sequence of causes. Thought experiments like Wigner's friend push on what a fact is. If one observer inside a lab sees a definite result, while an outside observer treating the whole lab as a quantum system still assigns it a superposition, then whose account counts as the single reality? The measurement problem asks how possibilities become one outcome. Wave functions give probabilities that match data with great accuracy, yet the theory does not spell out a unique, observer-free rule that turns spreads of possibilities into a single result. These issues are not side notes. They sit at the center of the theory's meaning. Despite that, quantum mechanics works with remarkable precision. It predicts energy levels in atoms, scattering rates in particle experiments, and the behavior of semiconductors. Superconductors, lasers, LEDs, and MRI scanners follow from it. Your phone, the internet backbone, and GPS all depend on quantum effects modeled correctly. Engineers do not need to settle philosophical debates to build devices. The math delivers. Still, the success of the math does not answer what the math says about the world. Different interpretations, ways to read the theory, attempt to fill that gap. Some say the wave function is all there is, and reality branches into many outcomes. Some say hidden variables set definite properties, but must be non-local, meaning linked in a way that does not fit simple nearby causes. Others treat the wave function as a tool for organizing knowledge rather than a physical object. Each path keeps the predictions but changes the picture of what is real, of what counts as cause, and of what an observation is. None has won a final vote. The reason is simple. Experiments settle numbers, while interpretations arrange meaning around those numbers. Consider entanglement. It is not just spooky by nickname. It violates Bell inequalities, which are mathematical limits any local hidden variable picture must obey. Lab tests with photons, electrons, ions, and even larger systems have closed major loopholes and still show the same result. Quantum correlations beat those limits, yet they do not allow faster-than-light signals. The statistics keep causality safe in the sense that no usable message jumps ahead, but the shared structure between distant outcomes remains beyond classical explanation. Or, look at interference. When single particles pass through an interferometer, patterns build up as if each particle sampled multiple paths. Then the pattern changes when which path information becomes available, even if that information is later erased in a setup designed for that purpose. The effect is about information in the experimental arrangement, not about a conscious observer or about sloppy gear. These are careful, controlled facts. At the same time, our everyday success with classical thinking is not wrong. It is limited. When huge numbers of particles interact with their environment, quantum phases those delicate relations that create interference spread out and effectively vanish from view, a process called decoherence. Decoherence explains why tables feel solid and why a baseball follows a clean arc, even though, in principle, it is made of quantum parts. It does not, on its own, choose a single outcome. It tells us why alternatives stop interfering and why classical behavior emerges as an excellent approximation in the world we touch. This bridge helps, but does not end the measurement problem. It shows why we usually see definite results without telling us how definiteness is selected in each single run. Another source of confusion comes from language. Words like particle and wave carry images from classical life. In quantum theory, the basic object is a state that evolves smoothly and gives probabilities for outcomes. The state is not a tiny marble or a ripple in a pool. It is a catalogue of what can be found if a certain measurement is made. Choose a different measurement and the catalogue changes. This is not license for anything goes storytelling. It is a rule. Outcomes and their probabilities depend on the full experimental context. When two contexts cannot be combined, when the measurements exclude each other, trying to force a single, hidden list of pre-written answers leads to contradictions with experiments. The world at small scales does not carry that kind of list. Even gravity enters the story through the black hole information paradox. Quantum theory says information cannot be destroyed, yet early views of black hole evaporation seemed to erase it. New work using quantum field theory, holography, and ideas from quantum error correction suggests that information could be hidden in subtle, long-range correlations and, in principle, recovered. The full, universally accepted account is still being built, but the lesson is clear. Quantum puzzles are not just lab curiosities. They reach into space-time itself and shape what a complete physical theory must explain. From that cosmic backdrop, the tension narrows to the core of quantum theory: measurement. For over a century, Physicists have predicted outcomes with stunning accuracy, yet the theory stays quiet about what the world is like between observations. The math gives procedures. Prepare a system, let it evolve, compute probabilities, read a result, but it does not settle what a particle is, why outcomes appear as single clicks, or what exists between one detection and the next. This gap, precise numbers without a shared picture, breeds paradoxes whenever we turn calculations into claims about reality. Do properties exist before we measure them? How do distant systems stay linked? Does time only flow forward at the smallest scales? When we push past recipes and ask for an explanation, we meet conflicts. Some are logical tensions. Some are clashes with everyday intuition. None of this sits on the fringe. The architects of the theory wrestled with it. A leading voice of the last century admitted that understanding quantum mechanics in the usual sense may not be possible. Another warned that if the theory does not unsettle you, you have missed it. A pioneer of black hole physics has said the framework makes no ordinary sense. Einstein, who helped launch the quantum era with light quanta, argued that the description must be incomplete. He wanted a deeper story with definite facts underneath. Schrödinger, who wrote the central wave equation, later worried about the implications of his own work. These were not people allergic to new ideas. They built the tools, verified the predictions, and still found the meaning unclear. That uncertainty continues, even as the evidence grows. Today we can entangle ions in traps, photons in fibers, and superconducting circuits on chips. We can shield experiments from noise, switch settings at high speed, and close loopholes that once left room for classical explanations. The patterns remain. Quantum mechanics works, down to many decimal places, yet basic questions remain open. What exactly is a measurement? Is the wave function a physical object, a catalog of knowledge, or something else? Do unobserved systems carry definite values, or do values arise only in specific measurement contexts? How do quantum statistics give rise to the stable, classical world we inhabit? These are not academic ornaments. They touch the core of science, which aims not only to predict, but to explain. Consider entanglement. Two particles can be prepared so that their outcomes are strongly correlated even when measured far apart. Tests of Bell inequalities show that no theory with only local, pre-written instructions can reproduce these correlations. The violation does not allow faster-than-light messages. The statistics will not carry a useful signal. Still, the joint pattern exceeds what any classical story with nearby causes can deliver. Or consider delayed choice and quantum eraser setups. Interference appears or vanishes depending on whether which path information is, in principle, available, even when the choice to keep or erase that information is made after the particle has entered the device. The sequence does not send influence backward in time. It highlights that outcomes depend on the full experimental context, including what can be known. The measurement problem sits behind many of these puzzles. The wave function evolves smoothly by a linear rule that spreads possibilities. A measurement yields one result. How do many possibilities become one record? Some approaches add hidden variables that carry definite properties, though non-local effects then become unavoidable. Some split reality into many branches where all outcomes occur in separate, non-communicating sectors. Some say the wave function is a tool for computing expectations, not a material field, and that collapse is an update of knowledge. Others modify the dynamics so that superpositions spontaneously localize. Each option keeps the predictions where they have been tested, yet each draws a different map of reality, cause, and fact. Decoherence helps explain why quantum interference fades in large open systems. When a system interacts with its environment, delicate phase relations spread into many degrees of freedom. Interference terms become practically unobservable, and effective classical behavior emerges for macroscopic records like pointer positions. This explains why we do not see tables in superpositions. It does not, by itself, pick a single outcome in a single run. Decoherence is part of the story of classical appearance, not the full rule for definite results. The remaining step, why this result and not another, depends on which interpretation or extension one accepts. Language causes trouble too. Words like particle and wave come from older pictures. In quantum theory, the central object is the state, which encodes amplitudes for measurement outcomes. Ask a different question, measure a different observable, and the relevant description changes. Trying to assign a single, hidden list of pre-existing answers to all possible questions runs into hard limits set by the theory and by theorems that capture contextuality. The world at small scales does not behave like a box of labeled marbles waiting to be read. Gravity adds another layer. The black hole information problem puts quantum ideas beside curved spacetime. Early calculations suggested that black holes evaporate thermally, erasing information and leaving only featureless radiation. Quantum theory, however, tells us that information is not destroyed. Modern results hint that subtle correlations in the outgoing radiation and features of quantum geometry can preserve information, yet a fully agreed account is still in progress. The point is not to reach for drama. It is to note that quantum puzzles touch both the very small and the very large, pulling on the fabric of space-time itself. Because these tensions arise from the logic of the theory, better sensors alone will not erase them. Paradoxes here are not bugs from bad equipment. They are signposts showing where our concepts bend. In the history of physics, such signposts have pointed toward deeper frameworks. Confusion about planetary motions pushed Newton to set down new laws. Confusion about light and electricity led to relativity and the unification of space and time. Confusion about atomic spectra and heat radiation opened the door to the quantum. Paradox is not a wall. It is a junction where old paths meet limits. Quantum mechanics is unlikely to be replaced because it works too well across too many domains. The open question is what sits beneath or around it. A complete account might explain why the formalism has its structure, why probabilities take the shape they do, why measurements yield discrete outcomes, and how classical behavior emerges with the stability we see. It might tie information, causation, and space-time together in a clearer way. Or it might tell us that some intuitions about fixed properties, single histories, or a universal time order must be set aside in favor of rules that match the data, even if they unsettle our habits. None of this requires mysticism. The strange claims often heard in casual talk, mind over matter, messages to the past, anything goes, do not follow from the careful statements of the theory. What the careful statements do say is already strong. Outcomes depend on the measurement context. Joint statistics can exceed classical bounds while respecting no signaling. Information constraints shape what patterns can appear, and probabilities come from amplitudes that add and cancel like waves. These are crisp, testable points that hold across platforms and experiments. As we move through specific paradoxes, the plan is steady. Describe the setup, Note what classical reasoning would expect. Compare that to quantum predictions and to actual data. Identify which assumptions cannot all be true at once, then keep only the minimal set that experiments demand. This method avoids decoration and keeps attention on what is fixed by evidence. It also shows exactly where interpretations diverge, which helps sort claims into what is measured and what is a choice of worldview layered on top of the same numbers. Famous names will appear again, not as authorities to settle debates, but as markers in the development of ideas. When a leading figure insisted that nature is not ruled by chance, the statement was a push for a cleaner picture, not a veto on statistics. We now know that any hidden structure must be non-local or contextual, in a way that breaks classical expectations. When another physicist warned that failure to be shocked signals a lack of understanding, the point was to take the data seriously, even when they push language to its edge. The lesson is simple. Hang on to the experiments, treat interpretations as scaffolds, and keep definitions tight. The practical side remains strong. Quantum devices exploit superposition and entanglement to sense tiny forces, secure communication channels, and speed up certain calculations. These successes underline the same rules that raise philosophical questions. Using a resource does not settle what it is, but it clarifies which features are operationally real. Interference can be turned on or off by controlling which information can exist in principle. Entanglement can be shared, traded, and consumed like a resource in protocols. Context is not a slogan. It is a design constraint. Open questions are precise, not vague. What objective structure, if any, underlies state vector reduction? How do quantum probabilities link to frequencies in long runs without adding assumptions beyond the formalism? Can space-time itself emerge from entanglement patterns in a concrete, testable way? Is there a clean boundary between quantum and classical, or only a scale where interference becomes practically unreachable? Such questions guide both theory and experiment, shaping new tests that push loopholes closed and extend quantum behavior to larger scales and longer times. The goal here is not to settle all meaning at once. It is to map the pressure points with care. Where calculations and measurements agree, we mark firm ground. Where everyday concepts fail, we mark the limits and adjust the language. Where multiple interpretations survive the same data, we label the fork and keep both paths in view. Step by step, the landscape becomes usable, even if it stays odd. We keep to operational facts, preparations, measurements, and the patterns they produce. To look under the quantum veil, we begin with a clear, testable setup. The delayed choice quantum eraser is an extension of the double-slit idea, but with an added layer that controls whether which path information exists in principle. Think of single photons traveling one at a time toward a device that offers two paths. If no device can reveal the path, the photon behaves like a spread-out wave, and the detections, collected over many trials, form an interference pattern. If a device can reveal the path, even if no person checks the readout, the interference vanishes and the detections add up like two simple piles. That is the core rule. Interference appears only when which path information is unavailable. The eraser version couples each photon to a partner that acts like a label. Often, these partners are created together in a crystal that splits an incoming photon into two lower energy photons. One, called the signal, heads to a screen where its position is recorded. The other, called the idler, takes a longer route through beam splitters and detectors that can either keep or erase the path label. Importantly, the signal can be recorded first at a detector screen, while the idler is still on its way. Only later do we choose a measurement on the idler that either preserves which path information or erases it. After all detections are done, we look back at the list of signal positions and sort them into groups based on what happened to their idlers. When the idler's measurement preserves which path information, the matching group of signal detections shows no interference. When the idler's measurement erases that information so that no path can be known even in principle, the matching group of signal detections shows interference. If you combine all signal detections without sorting, the overall pattern on the screen is a simple blur with no fringes. The interference only appears inside the properly sorted subsets, which are revealed by comparing time tags between the two detectors. This comparison step is called coincidence counting. It is bookkeeping, not magic. It lines up which signal photon goes with which idler result. This is why the experiment does not let anyone send a message to the past. You cannot look at the live screen and tell from its raw pattern which choice will later be made on the idler. The screen by itself shows no fringes. Only after the idler results arrive can you divide the screen data into the kept path subset and the erased path subset. In one subset, the fringes show up. In the other, they do not. The statistical structure is what changes, not the locations of spots already recorded. No dot moves after the fact. What changes is our grouping of dots by the later outcome of the idler measurement. To see the logic cleanly, it helps to clarify three ideas. First, superposition means the quantum state carries amplitude for multiple alternatives at once. For the two-path device, the state includes both paths. Interference is the rule that amplitudes can add or cancel, which creates bright and dark bands in detection rates. Second, which path information means that, in principle, a measurement exists that can reveal the path without ambiguity. Once such information is available, the alternatives stop interfering. The statistics become additive rather than wave-like. Third, entanglement means the signal and idler share a joint state so that learning something about the idler tells you something about the signal. The eraser uses entanglement to control whether path information exists or is scrambled beyond recovery. A standard layout uses a nonlinear crystal to create entangled photon pairs. The signal goes straight to a position-sensitive detector, often labeled D0. The idler travels through a set of beam splitters and mirrors to one of several detectors, say D1 through D4. Two of those detectors correspond to erasing which path information because the optical paths are arranged so that the idler's final state mixes the two possibilities in a way that makes the path unknowable. The other two detectors preserve which path information because their outputs remain tied to a definite origin path. The delayed choice comes from placing long optical delays or fiber loops in the idler arm so that its detection occurs after the signal has already been recorded at D0. When the data are analyzed, the signals matched with the eraser idler outcomes show complementary interference patterns. In many versions, one subset shows fringes and the other shows anti-fringes, two shifted patterns that cancel out when combined. This cancellation explains why the unsorted screen shows no fringes. The presence or absence of interference, then, is not a property of the signal detections taken alone. It is a property of correlations between signal positions and idler outcomes. The experiment does not rewrite history. It classifies history based on a later tag. The disturbing feeling comes from time order. The signal seems finished when it hits the screen. Yet only later does the idler measurement determine whether the signal's subset will reveal fringes. One way to reduce the tension is to think of the entire setup source, paths, beam splitters, detectors, and time tags as a single quantum process with inputs and outputs. The quantum state evolves through the whole network. Outcomes are joint events recorded across devices. In this view, there is no need for influences going backward in time. There is a need to respect that quantum predictions refer to joint probabilities conditioned on the full measurement context. Another way to talk about it uses the idea of complementarity. Path, knowledge, and interference are complementary. The more you can, in principle, know about which path, the less visibility the fringes have. The eraser does not restore a lost pattern by undoing a disturbance. It removes, in principle, the information that would have allowed the path to be known. And with that information gone, interference becomes possible again in the correlated subset. The key phrase is, in principle. Even if no one looks at a record, the mere possibility of learning the path can be enough to block interference. Some interpretations add stories around these facts. A time-symmetric account treats the experiment as constrained by conditions at both the source and the final detectors, with probabilities depending on boundary data from past and future ends of the process. A many-worlds account says that detection branches the world into non-communicating outcomes. The sorting simply groups records from branches where the idler landed in particular detectors, revealing fringe structures within those branches. A hidden variable account would need non-local features to match the correlations while avoiding signaling. An information-based view treats the wave function as a tool for inference. Collapse is an update to knowledge, conditioned on outcomes, and the eraser's sorting is a textbook case of conditional probabilities, revealing structure that is invisible in the marginal totals. Each view preserves the no signaling rule and reproduces the same counts. A common misunderstanding is to picture the detector at the screen as forcing the photon to choose, and then, later, the eraser somehow reaching back to change that choice. The better picture is that the screen records one piece of a joint event. The later idler measurement supplies another piece. Only when the pieces are combined in the right way do interference terms become visible. This is ordinary in probability theory. Two variables may show no pattern in their separate distributions, but reveal strong structure in their joint distribution after conditioning. The quantum twist is that the structure tracks the availability of path information, not mechanical disturbance. It is also important to separate human attention from physical records. The setup works the same whether anyone is watching in real time. What matters is whether the lab arrangement allows the path to be known. If a detector writes the path data to a device, and that device is later destroyed so that no one can, even in principle, recover the record, the interference can reappear in the correlated data. If the data survive in any form that could, in principle, be read, the interference is gone. The experiment is a lesson about information flow, not about minds steering outcomes. Variations of the eraser show the same logic, with different hardware. Some use atoms instead of photons, with internal states acting as path markers. Some use polarization labels as the which path tag, and polarizers as the eraser. Some push the time order so far that the idler is measured in a separate lab with synchronized clocks. Across these designs, two facts persist. Interference appears only in subsets where path information is erased, and the overall unsorted record at the first detector never shows fringes by itself. This is the operational content, and it is enough to remove claims about messaging to the past while keeping the genuine oddness intact. The setup also underlines the role of context. A witch path measurement and an interference measurement are different questions asked of the same source. You cannot have maximal answers to both at once. Trying to imagine a hidden ledger that lists both answers for every run leads to conflicts with the observed correlations. The eraser lets us switch which question is effectively asked of the joint system, even after one part has been recorded. By choosing how the partner is measured and how the data are sorted, from a practical view, the eraser is a tool. It shows how to control interference by controlling information. In quantum sensing and communication, similar ideas let engineers tune visibility, protect coherence, and route correlations where they are needed. The lesson is not that causality is broken, but that quantum predictions belong to full experiments with defined inputs and outputs. Partial views can look classical. Conditioned views can reveal hidden wave structure. Because the effect depends on sorting with the idler outcomes, there is always a delay between recording the screen and seeing any fringes. No observer can decide later to erase or keep the path and have the unsorted screen change. This delay protects causal order at the level of usable signals. At the same time, the dependence on later choices challenges the simple picture that events carry fixed, observer-independent histories. The history that is meaningful for prediction is a joint one, spread across the devices that take part in the measurement context. Questions remain sharp and testable. What are the minimal physical conditions that count as path information in principle? How small can the idler's trace be and still destroy interference? How far apart in time can the signal and idler detections be while the correlations remain robust? How do noise and loss in real fibers or crystals change the visibility of the fringes in the sorted subsets? Each of these can be addressed by changing components, measuring contrasts, and checking that the no signaling rule holds. With these points set, the delayed choice quantum eraser stands as a clean case study. It shows how superposition, entanglement, and information flow decide whether interference appears. It shows that sorting by later outcomes can reveal patterns hidden in raw totals. It shows that quantum predictions to respect operational causality while reshaping our ideas about history and context at small scales. We proceed by specifying sources, paths, detectors, and the sorting rules used to analyze the counts. The delayed choice quantum eraser shows that a measurement is not a single moment but a chain of steps. The choice to keep or erase which path information can be set after the first detection, yet the sorted data still track that later choice. In plain terms, the availability of path information that could, in principle, tell us which route the photon took, changes the statistics, even when the screen has already recorded a spot. The wave-like or particle-like signature is not fixed at the split. It depends on the entire arrangement, including the later measurement on the partner photon. This pushes against the classical rule that the past is complete and sealed once an event has happened. In everyday physics, causes sit in the past and never wait for the future. Here, the usable signals still respect that order, but the correlations remind us that quantum descriptions depend on the full context. This does not mean dots move after they appear, or that we can signal to the past. The raw screen, taken alone, never shows a clear fringe. Only after we pair each screen hit with the partner's later outcome do patterns emerge inside the subsets. The point is subtle. The theory gives exact predictions, and the lab confirms them. Yet a simple story of what physically happened along the way remains hard to write. Translate the math into pictures, and the pictures strain our habits. One picture leans toward retrocausality, where future and past boundary conditions both matter for quantum events. Another treats the wave function as a global object that covers the whole setup across time, with a definite history appearing only when all records are in place. A third keeps to information. Quantum states encode expectations, and updating on later data reveals structures that were invisible in the totals. Each picture keeps the no signaling rule and matches the counts. Each asks us to loosen a different intuition about time. This is why the delayed choice eraser carries weight. It is not a gap in technology or a mistake in analysis. It is a controlled test that challenges the idea that what happened is a single, observer-independent track fixed at the moment of impact. It suggests that the past, as described by quantum rules, may be conditional on the web of measurements that define the experiment. Some people find that view flexible and elegant. Others see it as a warning that our causal picture is only approximate. Preference aside, the records agree. Run the setup, sort the events by the later choice, and you get the same clean split between interference and no interference every time. Try to turn those records into a plain narrative, and you face a list of options, none fully comfortable. Retrocausality says later conditions partly fix earlier quantum descriptions, though not in a way that lets you change outcomes or send a message. Time-symmetric models use equations that look the same forward and backward and assign probabilities with input from both ends. Many worlds puts each outcome in a separate branch, and the post-sorting simply groups data from branches with the same partner result. Objective collapse models add new dynamics that randomly pick a single outcome. Then, the eraser's behavior must be reproduced by how and where collapses occur. Psi epistemic views say the wave function is a state of knowledge, and conditioning on the idler readout is just Bayesian updating in a quantum setting. None of these stories breaks the numbers. All keep the same tables of coincidences. If the eraser questions how time and information fit together, Wigner's friend questions what we mean by a fact. The setting is simple to describe. Picture an isolated lab containing a quantum system, like a spin that is in a superposition of up and down. A scientist inside the friend measures the spin and records a definite result. From the friend's point of view, the superposition is gone. The record reads, for example, up, and the world inside the lab includes a notebook, a memory, and a pointer, all aligned with that result. Standard rules, applied locally, say the state has collapsed. Now step outside the lab with Wigner. He has not looked in, has not interacted with the lab, and keeps the lab isolated. According to quantum mechanics, he is free to treat the entire lab, the spin, the device, the friend, and the written record as one big quantum system. If he does that, the combined system remains in a superposition. One branch where the friend saw up, and one branch where the friend saw down, each correlated with matching records and brain states. From Wigner's view, before he opens the door or couples a device to the lab, no single outcome has been selected. The friend's definite experience and Wigner's superposed description both follow from applying quantum rules to different cuts of the world. This raises a direct question. Do two valid observers have to agree on what has happened? In classical physics, the answer is yes, because the world carries facts that do not depend on who checks them. In the Wigner picture, agreement is not guaranteed until interaction occurs. the friend's memory is definite inside the sealed lab. Wigner's description is a superposition outside it. These are not merely different levels of ignorance. They are different state assignments that the formalism allows when observers have not exchanged information. If Wigner performs a special interference test on the whole lab, something only possible in principle, with perfect isolation, his result could, in theory, reveal coherence between the up and down branches, a signature that from his perspective, no collapse happened. That possibility conflicts with the friend's local story of a completed measurement. It is tempting to say, this is just missing information on Wigner's side. Quantum theory blocks that move. The superposition in Wigner's description is not a placeholder for an unknown fact. It is a live state that, in principle, can produce interference effects if the lab is treated as a quantum object. Only when Wigner later interacts with the lab and learns the outcome, do both observers share a single, aligned record. Before that exchange, each account is internally consistent and anchored to its own interactions. Over the years, the thought experiment has been sharpened with explicit protocols that replace conscious observers by well-defined quantum memories and devices. Versions with small systems have even been tested in limited forms, pushing on whether different observers, in the technical sense of record-holding systems, can assign different states without contradiction. The original, human-centered version, however, stayed in the realm of philosophy for a simple reason. We cannot isolate and recombine a laboratory containing a conscious person as if it were a photon or an atom, and we cannot put an actual human observer into a controlled quantum superposition. Physicists have learned to test the logic of Wigner's idea without putting a human into a fragile superposition. They build friends from controlled quantum systems, small registers that can store a result, act on it, and later be measured from the outside. In 2019, a team reported a tabletop design in which two pairs of entangled particles were measured by such stand-in observers. The layout let each friend inside assign a definite outcome, while two outside observers playing the role of Wigner could still perform tests sensitive to coherence across those outcomes. Under specific settings, the data matched a pattern where the inside records and the outside interference signals were both present. The numbers did not point to sloppy detectors or missing calibration. They matched quantum predictions that allow incompatible descriptions to coexist until information is exchanged. The idea is simple, even if the hardware is careful. Start with entangled particles. Route one particle of each pair into a device that plays the friend. It interacts with the particle and stores result A or result B in a quantum memory. From the friend's point of view, a measurement has happened. The other particle of each pair can be held or sent along a different path. Later, an outside observer can choose between two kinds of tests. One kind reads the friend's memory as if it were a classical record, asking, "Which result did you store?" The other kind performs an interference measurement that only works if, from the outside perspective, the joint system particle plus memory still carries coherence between alternatives. By scanning settings and comparing coincidence counts, the experiment checks whether the outside observer can reveal interference even when the inside device already holds a definite record relative to itself. In some runs, the results fit standard expectations where reading out the memory kills interference. In other runs, the settings reveal a different pattern. Interference signals appear for the outside observer, while the inside friend still holds a record consistent with a definite outcome from its own frame. The lesson is not that both parties are reading the same bit differently. They are asking different, incompatible questions of a shared quantum system. The friends question, what was the outcome? And Vigner's question, is there coherence across outcomes? Do not commute, which means the order and context of measurements matter. Quantum mechanics lets both kinds of regularities show up, but not in the same conditional slice of data and not for the same cut through the system. This pushes on the idea of a single, global story with observer-independent facts. If the friend assigns spin up and writes it to a memory, that is a definite event relative to the friend. If Wigner treats the whole lab as a quantum system and demonstrates interference between up and down branches, that is a definite event relative to Wigner. Neither party is mistaken within their own interaction history. Agreement arrives only when they exchange information and bring their descriptions into contact. Until then, the theory permits different, correct, state assignments tied to different observers and different measurement contexts. How can that be? One answer uses the many worlds picture. In that view, the friend splits into branches, one with up, one with down. Wigner's outside test probes coherence between those branches before his own interaction branches him. The price paid is a landscape of non-interacting branches and a rule that probabilities come from their weights. Another answer is relational quantum mechanics. It says that all quantum states are relative descriptions. The friend state for the spin and memory can be sharp, while Wigner's state for the combined lab can still be a superposition with no contradiction because there is no view from nowhere to compare them. The cost is giving up a single God's eye account. A different route, the Copenhagen family of ideas, puts a cut between system and apparatus and treats measurement as a primitive step where outcomes are created. But then one must say where the cut sits and why, or accept that it shifts with experimental aims. Objective collapse models add new dynamics that makes superpositions of large systems break down by themselves. Then the challenge is to match every interference test without fine-tuning. Psi-epistemic views treat the wave function as organized knowledge. Collapse is updating, and Wigner's interference is a lawful pattern of conditional probabilities rather than a peek at parallel realities. These choices are not wordplay. They change what we count as a fact and what it means for records to exist. The lab versions of Wigner's friend use qubits and photons that stand in for notebooks and memories. A record, in this setting, is any stable correlation that could be read out. When a device stores up, it becomes entangled with the particle, and often with nearby degrees of freedom. Relative to the device, the outcome is fixed. Relative to an untouched outside frame, coherence can remain and be revealed by the right joint measurement. Lose that coherence by leakage to the environment, and the outside interference test fails, bringing both descriptions into classical alignment. This is decoherence at work. Phase information spreads into many places and becomes practically unrecoverable, so only classical-like records remain useful. It helps to separate two tasks, predicting counts and telling stories. The predictions come from the same linear rules that also underlie interference and entanglement. The stories are ways to picture what the rules imply about reality. Wigner's friend is a sharp test because it drives a wedge between two seemingly basic claims, that measurements produce observer-independent facts, and that the quantum state for a large, isolated system should evolve unitarily, keeping coherence. Keeping both claims at once runs into trouble when the outside observer can, in principle, detect that coherence. Giving up either claim avoids the clash. but each choice has consequences for how we talk about truth and objectivity. Some modern proposals try to frame the issue in device-level language. Treat an observer as any system that can acquire, store, and later report information. Then ask, which sets of stored facts can coexist without contradiction when probed by different external tests? The answer comes back contextual. Fact A relative to device X and fact B relative to device Y may not fit into a single global list if X and Y interact with the system in incompatible ways. The incompatibility is not about opinion. It is about the algebra of the measurements and the order in which interactions happen. This bears on the measurement problem. If collapse is a single, objective event, there should be a unique point where superposition ends and a fact begins. Wigner's friend's scenarios make that point hard to place without ad hoc rules. If collapse is relative or emergent, tied to information flow and decoherence, then different observers can assign different states until they interact and compare notes. In that case, fact becomes tied to a network of correlations rather than a single global ledger. The mathematics already treats outcomes as conditional on the whole setup. The friend experiments show how far that conditional structure can be pushed without breaking predictions. The topic brushes the question of consciousness because Wigner's original story used a human friend. Modern tests avoid mind, talk, and focus on records. A qubit can be a friend if it stores and reports. The odd features remain. Conscious awareness is not needed to produce the effect, and removing it keeps the discussion on operational ground. Still, the original motivation lingers. If a person inside says, "I saw up," while an outside description keeps the lab in a superposition, how do we reconcile these reports? In practice, we do so by opening the lab and comparing. Before that exchange, the theory allows both state assignments to live side by side, each tied to its own interactions. This line of work links to other no-go theorems that limit classical ways of thinking. Bell's theorem rules out local hidden variables. Koch and Specker rules out non-contextual value assignments to all observables at once. Recent no-objective facts style inequalities formalize the tension highlighted by Wigner's friend. If you assume a single set of observer-independent outcomes and allow for certain quantum predictions, you hit a contradiction. Experiments with photonic qubits have tested versions of these inequalities, finding violations that track the quantum model. The details depend on how one defines an observer in hardware, but the trend is consistent. Quantum correlations resist a single, global catalog of facts that all observers must share before they interact. From an engineering angle, none of this blocks progress. Quantum devices already treat measurement as an interface that turns fragile amplitudes into robust bits. Designers protect coherence where needed and let it die where readout is required. What Wigner's friend adds is a warning label for language. Do not assume that measurements are simple stamps on a pre-written page. Outcomes are tied to contexts, and different contexts can support different, even incompatible, regularities. A system can carry records relative to one device, while still supporting interference relative to a larger, untouched frame. In day-to-day life, these distinctions blur. Decoherence is fast, environments are messy, and shared communication brings observers into alignment. Everyone ends up agreeing about tables and clocks because the world outside the lab destroys coherence quickly and spreads records widely. The thought experiment is valuable not because it changes daily practice, but because it marks where classical talk about facts stops being safe. It also guides new tests, isolate more of the lab, improve control over leaks, and ask ever more delicate questions about which records can coexist. Interpretations continue to divide along familiar lines. Many worlds keeps unitary evolution and spreads facts across branches. Copenhagen-style views keep single outcomes but treat the cut and collapse as primitives. Relational and cubist approaches keep outcomes but make them personal to the agent or device, with consistency enforced only when interactions occur. Objective collapse adds new stochastic dynamics to end superpositions. Hidden variable models accept non-locality or contextuality to match the statistics. Each scheme protects the core predictions and imposes trade-offs on what counts as real, common, and absolute. As quantum technologies scale, these issues gain practical edges. Distributed sensors, quantum networks, and error-corrected processors rely on careful handling of records and contexts. Protocols decide when to protect coherence and when to commit to outcomes, and they must account for who or what counts as having learned which result. Wigner's friend is not a roadblock. It is a map of where assumptions about global facts can lead to confusion if they slip in unnoticed. Retrocausality asks whether events can be influenced from both ends in time. In daily life, we place causes before effects and leave it there. Quantum theory resists that simple order. The basic equations are time-symmetric. They run just as well forward as backward. No built-in arrow tells the math which way time should flow. Delayed choice tests make this symmetry hard to ignore, because a choice made after a detection can still decide whether path information exists in principle for that run. The statistics line up with the choice, even though the earlier record at the screen stays fixed. The data do not carry signals to the past. Still, the clean match between late choices and early patterns invites a time-symmetric reading. A developed version of this idea is the two-state vector formalism. Standard quantum mechanics uses one state that evolves forward from an initial condition. Two-state vector adds a second state that evolves backward from a final condition. The system at a given time is described by both, like giving start and end boundary data for a single process. In this view, there is no abrupt collapse. What we call collapse is the point where the forward-evolving and backward-evolving states, along with the measurement setup, pick out a definite outcome. The rule is still linear and uses the same operators. What changes is the bookkeeping. Outcomes are constrained from both ends. Seen this way, the quantum eraser stops looking like a trick. The earlier signal detections and the later idler settings are both parts of the boundary data that define which correlations can appear in the sorted subsets. The forward state carries amplitude across both paths. The backward state, set by the later eraser choice, selects which combinations matter for the joint counts. No spot moves. The conditional patterns tighten because both conditions are in the model. This talk of backward evolving states raises worries about free will. If future boundary conditions matter, are choices fixed in advance? The formalism does not force a single story about agency. It says that the probabilities you compute at a time depend on which boundary data you include. Pick only initial conditions, and you recover the usual predictive rules. Add final conditions that match later records, and you recover the same joint statistics that appear in experiments. The approach is compatible with a block universe picture, where past, present, and future form a four-dimensional whole. It is also compatible with a weaker view that uses time-symmetric tools for inference, while leaving personal experience of choice untouched. The physics concerns correlations, not inner feelings. Retrocausality is not time travel. It does not allow messages to go to yesterday. No version that matches known experiments lets an agent change a recorded result or set up a paradox. The no signaling theorem still holds. What changes is the way we account for correlations. In time-symmetric accounts, a full description may use data from both ends. This is close to how boundary value problems work in other fields. Fix conditions at the start and at the finish, then solve for what fits both. In quantum theory, the fit shows up in conditional probabilities for measurement outcomes. This lens speaks to entanglement. When two particles are prepared in a joint state and sent far apart, measuring one lets you predict the other with strong accuracy. The pattern looks like faster-than-light influence if you expect only forward causes. In a time-symmetric story, joint outcomes are set by initial preparation and by the pair of later measurements taken together. Each side's local results still look random on their own. Only the joint table reveals the extra structure. Again, no signals pass between the labs. The extra structure comes from how the pair of boundary conditions constrain the pair of outcomes. Weak measurements offer another place where two-state ideas prove useful. A weak measurement is a very gentle probe that barely disturbs the system and is followed by a final, strong measurement called post-selection. Averaging over many runs gives a weak value that can lie outside the usual range of eigenvalues. In the two-state account, the weak value depends on both the initial state and the chosen final state, which clarifies why these unusual averages appear. The tool is limited but practical. It has helped map tiny optical shifts and amplify small signals in precision setups. None of this removes the need to define a measurement context. Retrocausal stories still rely on which observables are actually measured and which records exist. The approach does not make every odd claim true. It keeps the same operators, the same Born rule for probabilities, and the same constraints from relativity. It shifts where we place the weight of explanation, not on a one-way flow from past to future, but on a pair of constraints that meet in the middle. Objections focus on consistency. If backward evolving states matter, can they be chosen at will? They cannot. Final boundary data reflect actual later records, not arbitrary wishes. The model is descriptive. It mirrors what was measured, then shows how those measurements narrow the allowed histories. Another worry is that retrocausal talk smuggles in hidden variables. Time-symmetric accounts do not add extra local variables to dodge Bell's theorem. They keep the same non-classical constraints. The joint correlations still violate Bell inequalities and still obey no signaling. The difference is in how the causal book is kept. There is also the question of the arrow of time. Thermodynamics gives a strong arrow through entropy. Typical systems move from low entropy states to higher entropy states. That arrow comes from boundary conditions too, most notably a low entropy past. Quantum equations do not pick an arrow by themselves. The arrows we see connect to the specialness of certain boundaries and to how records form and persist. Decoherence helps here. When quantum systems couple to large environments, phase information spreads and becomes hard to recover. Stable, classical-looking records appear and tend to accumulate toward the future direction set by the growth of entropy. Time-symmetric rules can live with that. They say the micro-laws are neutral, while the arrows we use in practice come from the kinds of boundaries the universe actually has. Some researchers build explicit retrocausal models for simple systems. They assign influences that run along both time directions in a way that keeps the math local in space while being non-local in time. Others keep the two-state language without extra structure, and use it as a compact way to compute conditional probabilities. There are also proposals that merge these ideas with path integrals, where outcomes follow from summing over histories that obey both initial and final conditions. The test for all such models is the same. Match the statistics of known experiments and respect the speed limits of relativity. Critics point out that many puzzles can be handled without retrocausality by treating quantum states as tools for updating knowledge and by keeping careful track of which information is, in principle, available. In that camp, delayed choice setups are explained as changes in conditional descriptions as new data arrive, not as influences from the future. The two views use the same counts. They differ on how much metaphysics to accept in the story that runs under the counts. This is why the debate stays active. The numbers alone do not settle which story we should prefer. They only rule out stories that make wrong predictions. Even within a time-symmetric view, one must be precise about what is conditioned on what. It is not enough to say, the future affects the past. One must say, given an initial state and a later recorded outcome, the conditional probabilities at intermediate times change in a specific way. That statement can be checked against real devices. It can be used to design and test protocols, such as weak value amplification or certain metrology tricks that rely on post-selection. It keeps the discussion inside the lab frame, where terms like cause, record, and signal have operational meaning. The main practical constraint is the same as always. No device may produce a usable signal that outruns light, or that lets agents create paradoxes. Time-symmetric models respect that constraint by confining the role of future data to conditional updates that become available only after the relevant results are known. Before that, each party's local data follow ordinary statistics. After that, joint analysis reveals the same strong patterns that the standard rules also predict. Work proceeds by stating the boundaries, listing the measured observables, and computing the conditional probabilities that tie them together. Retrocausality can be used to explain the correlations of entanglement without faster-than-light influence. In that picture, each outcome is constrained by boundary conditions that include what is later recorded, so the match between distant results does not come from one lab signaling to the other. Both labs produce outcomes that are jointly consistent with the same future constraint. Locality in space is preserved, while influence is time-symmetric. The coordination is global across the trial, set by what was prepared and by what ends up being read. Skeptics answer that this only trades one surprise for another. Instead of asking how two space-like separated outcomes line up, we are asked how later facts can help fix earlier descriptions. They also ask whether such models can be tested. If retrocausality never permits a controllable signal to the past and only leaves statistical fingerprints that appear after the fact, it is hard to tell it apart from forward-only stories that reproduce the same data. Proposed tests tighten timing windows, control post-selection, and compare conditional probabilities, but no single experiment has forced a decision. The status is open. Workable retrocausal accounts exist alongside other interpretations that match the same counts. What keeps retrocausality on the table is the symmetry of the equations. The Schrödinger equation is time reversal symmetric. No preferred direction is built into the basic dynamics. Two boundary descriptions fit that symmetry in a natural way, like fixing both ends of a string before solving for its shape. Friction comes from experience, which does have a clear arrow. Coffee cools, smoke disperses, files corrupt rather than uncorrupt. That arrow connects to entropy. a statistical tendency for macroscopic systems to move from low entropy to higher entropy. At the level of isolated few particle systems, the laws are nearly reversible. If the arrow emerges from large numbers and environmental coupling, then time-symmetric accounts for small systems are less alien. They do not rewrite yesterday. They constrain allowed histories without enabling control over the past. Some groups develop explicit retrocausal models that keep space-local dynamics and allow influences to run in both temporal directions. Others adopt time-symmetric tools as compact bookkeeping, compute with initial and final data to get the same joint statistics. Critics prefer forward causal narratives or information-based readings where delayed choice effects are updates rather than backward influence. All sides accept the same guardrails. No superluminal signaling, no paradoxes, and agreement with laboratory counts. Entanglement is the stress test. Prepare two particles in a joint state and measure them far apart. Each lab sees random local results. When records are compared, the joint table shows correlations stronger than any local pre-written instruction strategy can produce. Bell's inequalities set the classical ceiling. Quantum experiments pass that ceiling while respecting no signaling. A retrocausal story says initial preparation and the pair of later measurements constrain the pair of outcomes without cross-room chatter. A non-retrocausal story says the joint quantum state and the chosen bases already fix the distribution. Adding future boundary talk is optional. Either way, the correlations are robust, and device-independent tests can verify them. These same correlations power what is nicknamed quantum pseudo-telepathy. No thoughts are read and no messages are sent. Players who share entanglement can win certain non-local games at rates unreachable by any classical plan that forbids communication. Picture a cooperative game. Two separated players receive questions drawn at random and must each reply with a single bit. A referee checks a rule that links both questions and both answers. The players may agree on a plan beforehand, but cannot talk during play. Classically, the best plan is a lookup table. Because the rule couples the answers in ways that depend on both questions, any fixed table fails on some inputs. There is a strict limit on the average score. In the CHSH game, that limit is 75% for uniform questions. In the Magic Square game, the limit is below 100%. With shared entanglement, the players do better. In CHSH, they can reach about 85.4%. That's Cyrilson bound. In the Magic Square game, they can hit 100% without communication. The nickname pseudo-telepathy comes from that perfect record. The structure is simple to state. The referee's rule forces a conflict if one tries to assign context-independent answers to all possible checks. Entanglement lets the players correlate their outputs by measuring shared quantum states in bases tied to their questions. Those bases are arranged so the quantum correlations satisfy all cross-checks at once, even though no single classical table could. No signal passes during play. The advantage lives in the joint statistics of measurements on a shared state that violates classical bounds while obeying no signaling. The Magic Square game shows this neatly. The referee picks a row for one player and a column for the other in a 3x3 grid. The row's answers must multiply to +1, the columns to 1, and the overlapping cell must match for both players. Classical tables cannot satisfy all 9 intersections. The parity constraints clash. Quantumly, the players share a specific entangled state and measure observables assigned to the chosen row or column. The algebra of those observables enforces the parity rules, and the overlap matches by construction. Perfect success follows without exchanging bits. This is not a loophole. It is a direct use of structure that local hidden variable models cannot reproduce. Bell's theorem rules out such models, and modern loophole-free tests support that verdict. Pseudo-telepathy games translate the theorems into a scoreboard with clear thresholds. Scores above the classical bound, with space-like separation, certify that a non-classical resource was present. Device-independent protocols use these violations to certify randomness or cryptographic keys, with security grounded in the impossibility of faking the quantum score using classical means. Retrocausality can sit alongside these games without changing the numbers. A retrocausal account reads the winning correlations as constraints from both ends of each round initial state and final measurements, rather than as instantaneous influence across space. A standard account reads them from the Born rule applied to the entangled state and the chosen observables. Both respect Tsirelson's bound and the no-signaling condition. Both require careful timing, fast, random choices, isolation, and verified independence between labs. What matters operationally is controlling context. In these games, a question maps to an observable and an answer to its outcome. Context determines which set of observables can be asked together, and quantum mechanics forbids a single list of pre-existing values that fits all incompatible contexts. That is why classical tables fail and entangled strategies succeed. The same lesson appears in delayed choice experiments and Wigner-style setups. Local streams look ordinary, while conditioned or joint data reveal non-classical structure. Laboratories implement the games with entangled photons, trapped ions, or superconducting qubits. They enforce space-like separation, switch measurement bases rapidly, randomize questions on the fly, and close side channels. Data are time-stamped and checked against classical, quantum, and no signaling bounds. When the win rate clears the classical ceiling by a safe margin, and known loopholes are shut, the conclusion follows. Entanglement was present and used as a resource. Seen next to the debate about time, the pattern stays steady. The same experiments can be narrated with retrocausal language, or with forward-only updates. The predictions match as long as the rules of the theory are applied to the full measurement context. The choice of story changes how we talk about cause and influence. It does not change which setups yield which joint tables. Work proceeds by stating sources, measurement settings, space-time separations, and the analysis that compares the joint results with classical ceilings and quantum limits. Imagine that before the game begins, you and your partner each take one particle from a pair, prepared in an entangled state. Entanglement means the pair is described by a single quantum state that spans both particles at once. They are not two independent objects with matching notes. They are parts of one system that has been spatially separated. When the referee sends you a question, you choose a measurement basis tied to that question and read a simple yes, no outcome from your particle. Your partner does the same at a distant station, using a basis tied to their question. No lights blink between rooms, no message is sent, and neither of you knows the other's choice or result. After the round, the answers are compared. The match rate beats any classical strategy that forbids communication. This is not just a story. Laboratories have run such games with photons, trapped ions, and superconducting qubits, logging timestamps and closing common loopholes such as slow setting changes or shared noise. The Magic Square game makes the logic concrete. There is a 3x3 grid whose entries must be either +1 or 1. One player is asked for a full row, the other for a full column. The rule demands that the product of any valid row equals +1, that the product of any valid column equals 1, and that the overlapping cell reported by both players match. If you try to pre-fill the entire grid with fixed plus or -1 values, you hit a contradiction. The row and column parity constraints cannot all hold, so a classical plan must fail on some inputs. With entanglement, the players share a specific quantum state and measure observables assigned to the chosen row or column. The algebra of those observables enforces the parity rules, and the shared state correlates the overlap cell. The players can win every round without exchanging any bits during play. A second case is the GHZ game, named after Greenberger, Horn, and Zeilinger. 3 players receive questions and must output answers whose products satisfy given parity checks. Classically, even the best prearranged table fails on some combinations. With a 3-particle entangled state and well-chosen measurements, the quantum strategy satisfies all checks with certainty. GHZ is striking because it shows a direct, all-or-nothing conflict with classical expectations. No averages or inequalities are required. The contradiction is built into the required parities, and the quantum rules fit them exactly. What sits beneath these wins is the structure of entanglement and measurement context. A classical table assumes each possible question has a pre-written answer waiting. That assumption tries to assign definite, context-independent values to several incompatible checks at once. Quantum mechanics forbids that move. Outcomes depend on which measurement you perform, and incompatible measurements cannot all have pre-existing values. Entanglement provides a joint state so that when each site chooses the right measurement linked to its question, the local random-looking answers align into global patterns no classical table can reproduce. The coordination is not messaging, it is correlation in a shared state prepared earlier and sampled in ways that expose structure only in the joint data. This is why the effect is called pseudo-telepathy. Looking at one player's answers alone, the stream is random. The special pattern appears only when the referee lines up both lists by question and time and computes the joint table. No information travels faster than light. Experiments enforce this by using fast, independent random number generators to choose settings, switching those settings quicker than a light signal could cross the distance between stations, shielding equipment, and verifying that no side channels leak information. When the win rate clears the classical ceiling by a safe statistical margin under these conditions, the conclusion is that a non-classical resource entanglement was present and used. The roots of the argument go back to Einstein, Podolsky, and Rosen, EPR, who in 1935 suggested that quantum mechanics must be incomplete if it avoids spooky action at a distance. They imagined hidden variables, extra facts carried by each particle that would restore definite properties and preserve locality. In the 1,960 seconds, John Bell translated that hope into precise limits. Any theory with local hidden variables must satisfy inequalities that cap the strength of correlations. Quantum mechanics predicts violations for certain states and measurement choices, and experiments have repeatedly observed those violations while closing major loopholes. The upshot is sharp. No local, realistic model with pre-written answers for all possible questions can match the data. Something in the classical picture must give way. There are distinct ways to make room for the data. One option drops locality and accepts non-local links that tie outcomes together without carrying signals. Another drops realism and says properties are not definite until measured in a particular context. A third keeps locality in the standard predictions, but drops counterfactual definiteness, the idea that unperformed measurements had definite values waiting. Each move preserves no signaling and matches experiments, yet each costs a familiar intuition about how the world should behave. Non-local games like CHSH show the trade-offs with a scoreboard. In CHSH, 2 players receive one of 2 possible questions each and return plus or minus 1 answers. The classical ceiling for the average score is 75% under fair random inputs. Quantum players sharing a maximally entangled pair can reach about 85.4%, that's Sirelson bound, and no quantum device can go higher. For Magic Square, classical strategies cannot achieve a perfect record. Entangled strategies can. These fixed ceilings and quantum advantages are not slogans. They are used to certify devices. If a system beats the CHSH ceiling with space-like separation and unbiased random choices, it demonstrates entanglement. If a pair of nodes wins the Magic Square game round after round without communication, it demonstrates a non-classical resource. This is the basis of device-independent cryptography and randomness generation, where security rests on violation of classical bounds rather than on exact knowledge of internal hardware. What then is an entangled pair really doing? The safe answer is operational. Certain joint properties belong to the whole system, not to the parts separately. Measurement on one part does not reveal a pre-existing value in the other for every possible setting. It fixes a relation consistent with both measurement choices. Change the settings and the correlation pattern changes in line with the shared state. The insistence on one global list of pre-existing answers produces contradictions with observed tables. Letting outcomes be contextual, tied to which measurements are actually performed, avoids those contradictions and matches the data. Interpretations add different narratives over this operational core. In the many worlds view, the entire setup particles, devices, observers, evolves unitarily with no collapse. Each possible outcome occurs in a separate branch, and the joint statistics reflect branch amplitudes. The perfect coordination in Magic Square and GHZ appears because within each branch, the local records match according to the global state's structure. In relational or agent-centered approaches, a state is always relative to an observer or device. Outcomes are facts for the system that registered them, and consistency across observers is achieved when information is exchanged. Objective collapse models modify the dynamics, so macroscopic superpositions decay spontaneously. They can recover the same non-local game scores if tuned correctly, while preserving no signaling. Retrocausal accounts keep locality in space but allow constraints to run in both time directions, so that initial preparation and later measurements together fix the joint correlations. The lab numbers constrain all these narratives to the same predictions. The narratives differ in what they ask us to give up conceptually. GHZ correlations amplify the lessons. With 3 players and a specific set of parity checks, any attempt to assign pre-existing plus or minus 1 values to all required measurements leads to an algebraic contradiction. The quantum strategy avoids the trap by using measurements whose operators may not commute in general, but are arranged so that the combinations actually used in each round do commute and match the parity rules. The result is not just higher than classical on average, it is perfect success where classical reasoning forces failure on some inputs. That clarity is why GHZ setups are used to diagnose genuine 3-party entanglement and to stress-test multi-qubit devices. Decoherence explains why these effects do not show up in daily life. In large, open systems, delicate phase relations leak into the environment and become practically unrecoverable. Stable, redundant records spread, and multiple observers quickly converge on the same macroscopic facts. In that limit, classical reasoning is an excellent approximation. Non-local games work because labs isolate small systems, protect coherence, choose settings quickly, and compare records with precise timing. When those controls are relaxed, the quantum advantage fades, and the world looks classical again. From a practical standpoint, the recipe behind pseudo-telepathy is an engineering guide. Prepare a known entangled state. Use independent, fast random sources to select measurement bases. Keep stations space-like separated and shielded. Record outcomes with accurate time tags. Analyze the joint distribution against classical ceilings and quantum limits. If the scores clear the classical bound and land where theory predicts, you have certified a resource. This method does not rely on internal trust in the devices. It relies on statistics that no classical system can mimic without communication. Set beside questions about time and causation, the picture is consistent. Whether one prefers a forward-only narrative, a time-symmetric account with boundary conditions, an observer-relative view, or branches with unitary evolution, the same operational rules govern these games. Context picks, observables, joint states set constraints, and no signaling keeps local streams uninformed about distant choices. The rest is interpretation layered over counts. Work proceeds by specifying sources, settings, separations, and the joint tables they produce. In one story of quantum mechanics, often called many worlds, measurements never collapse anything. The whole system evolves smoothly, and when a device records a result, the world splits into branches. In each branch, the records agree, because each branch is a closed, self-consistent history. The strong correlations in games and tests are then facts inside each branch. No superluminal message is needed because all parts, particles, devices, observers are pieces of one large state that follows the same rule everywhere. A different story is Bohmian mechanics. Here, particles have definite positions at all times. They move under guidance from a pilot wave, a real field defined by the same wave equation as standard quantum theory. The pilot wave is non-local. It depends on the full configuration of the system, even across distance. When particles are entangled, that guidance ties their motions together instantly. Realism is kept, positions are always definite, but locality is given up in a clear way. Relational quantum mechanics takes another line. A quantum state is not absolute. It is always relative to an observer or system. Each player in a game has a description tied to their own measurements. Those descriptions must agree when information is exchanged, and the consistency rules generate the correlations. There is no single God's eye state shared by everyone. There are only states relative to particular interactions, stitched together when observers compare notes. These stories disagree on meaning, but they leave the laboratory facts unchanged. Entanglement produces correlations that beat any classical plan without communication. The effect is operational and has uses. In quantum cryptography, two distant devices share entangled pairs and test their correlations. Any eavesdropper that taps the channel changes the statistics and gets caught. In quantum computing, entanglement links qubits, so algorithms can explore structured sets of possibilities in ways classical bits cannot. The advantage is not vague. It shows up as fewer steps for specific tasks, better sensing in noise, or stronger guarantees in security proofs. The philosophical pull is that entanglement looks like connection beyond space. Two detectors can show linked results, while neither stream alone carries a signal. The joint description belongs to the pair as one system. Space separates the hardware, but some properties are carried by the whole. That idea pushes against the picture of a world made only of separate things with fixed, private traits. Quantum tests say some traits are relational. They arise in the match between settings and outcomes, not as hidden entries waiting on a list. This line of thought leads to another odd result that has been tested in the lab: the quantum Cheshire cat. The nickname comes from a cat that can vanish while leaving a grin behind. The quantum version is not a trick with props. It is a careful interferometer study that uses weak measurements to separate, in a precise sense, where a particle seems to be from where one of its properties seems to be. The usual platform uses neutrons. A neutron is a particle with mass, no net electric charge, and a quantum property called spin. Spin is not a tiny ball turning like a toy. It is a built-in angular momentum that can point along directions we choose to probe, and measurements return discrete values. In the setup, a neutron beam enters a crystal interferometer that splits the wave into two paths. Inside the device, the neutron is in a superposition of both routes. If left alone, the two parts later recombine and can interfere, just like light in a Mach-Zehnder interferometer. To ask, where is the neutron? And where is its spin? Without crushing the superposition, the experiment uses weak measurements. A weak measurement is a very gentle probe. It shifts a pointer like a tiny phase, a small polarization tilt, or a minute beam deflection by an amount so small that any one run tells almost nothing. But by repeating the run many times and averaging, one can estimate a weak value, a number that reflects the system conditioned on how it was prepared, and on a later, strong measurement called post-selection. Because the coupling is gentle, interference is not destroyed, and information can be gathered about trends that would vanish under a projective, all-or-nothing measurement. In the Cheshire cat layout, the interferometer is tuned so that final detectors only click when the waves from the two paths recombine in a selected way. Along one path, a weak path-tagging device couples to position. Along the other, a weak spin probe couples to the spin component of interest. When the data are sorted by the final clicks that pass the post-selection, the averages tell a curious story. The weak where pointer points to one arm, as if the neutron traveled there. The weak spin pointer points to the other arm, as if the spin went that way. The pattern is consistent with position weight concentrated in one path and spin weight concentrated in the other for the subensemble that reached the chosen output. Spelled out carefully, nothing has split a neutron into two pieces. The strong final detection always finds a whole neutron at one detector or the other. The claim is about where different kinds of weak signatures show up when you condition on the same post-selection. The position-sensitive weak probe registers mainly on one arm, while the spin-sensitive weak probe registers mainly on the other. The numbers can even take on weak values outside the usual range, a known feature of weak measurements when pre- and post-selected states are nearly orthogonal. These are averages over many runs, not single-shot maps. They are features of correlations set by the full interferometer and the selected output. This separation has a simple reason in the math. In an interferometer, you can arrange the relative phase and internal rotations so that, for the selected exit, the amplitude linked to position information lives mostly in one arm, while the amplitude linked to spin information is encoded in the other. Weak probes couple to those amplitudes and report where each kind of weight sits for the conditioned subensemble. Change the phases or the post-selection port, and the pattern shifts. The effect depends on both the gentle probes and the final filter, not on a particle splitting like a toy. The result is strange if we insist that properties must ride with objects like stickers on a suitcase. Quantum mechanics does not require that rule. It allows properties to be spread across paths and encoded in internal degrees in ways that only show up when questioned with the right probes and sorted with the right post-selection. The neutron behaves like a quantum state with parts, spatial parts along the interferometer arms, and internal parts for spin. Different questions reach different parts. Position like weak couplings read spatial weight. Spin like weak couplings read internal weight. Under tuned conditions, those weights sit on different arms for the same conditioned set of runs. The technique depends on staying weak. A strong position measurement would pick a path and kill the interference that makes the effect visible. A strong spin measurement in the middle would also spoil the relations needed at the recombination stage. That is why the apparatus uses tiny couplings and gathers statistics over many identical neutrons. The weak probes add small shifts to meter variables. The post-selection filters run so that the final state matches a target. Only then do the averaged pointers tell the story about where position weight and spin weight seem to be for that target set. Variants replace neutrons with photons and spin with polarization, or use different internal states in atoms. The same logic applies. Gentle probes touch one aspect on one path and another aspect on the other path. The post-selection chooses an exit where interference conditions produce clean, weak values. In each case, the apparent separation of object and property is a statement about how information is distributed in the quantum state under the chosen conditions. It is not a license to imagine a free-floating spin roaming a beamline without a particle. This kind of experiment matters for more than its odd name. Weak probes are tools for precision metrology. They can amplify tiny effects by selecting rare outcomes where small shifts add coherently. They also help map fields, phases, and couplings inside interferometers without wrecking the very interference being studied. In foundational work, they give controlled ways to ask counterfactual sounding questions. Where would a trace show up if we ask this or that, while keeping the rules clear? Prepare, weakly couple, post-select, and average. Language still needs care, saying, the spin went left while the neutron went right, is shorthand for a structured set of weak values tied to a specific pre- and post-selection. Change the selection and the statement may reverse. The effect is real in the sense that the averaged meter shifts are measured and match calculations. It is not a picture of parts flying apart in the classical sense. The safe takeaway is operational. Interferometer phases and internal rotations can park different weak signatures on different paths for the same conditioned ensemble, and weak measurements can read those signatures while leaving the interference needed for the post-selection largely intact. Weak measurements keep an interferometer's superposition intact long enough to read faint traces, so the apparent separation of object and property can be seen in averages. The probe is gentle by design. A tiny interaction nudges a meter variable phase, polarization, or position so slightly that a single run tells almost nothing. Many identical runs are needed. Critics argue that the resulting weak values are conditional and can even fall outside ordinary ranges, so treating them as literal locations of a particle or its spin reads too much into statistics. They say the meters report how the pre-selected state and the chosen post-selection jointly weight different paths and internal degrees of freedom. That is a statement about a quantum state, not a map of intrinsic, transportable traits. Supporters answer that this is exactly what the formalism predicts and that the meters couple to the state in a defined way. If position weight shows on one arm while spin weight shows on the other for the same conditioned subensemble, then properties can be distributed across space and internal structure in ways that have no classical counterpart. The disagreement mirrors a larger pattern in quantum foundations: common ground on calculations, distance on meaning. Everyone can write the same amplitudes and phases for a neutron interferometer, place the same weak couplings on the arms, and compute the same pointer shifts. Everyone can watch those shifts flip sign. When phases or post-selection ports are changed, the gap opens when turning those numbers into a picture. One picture says, the particle traveled right, while its spin traveled left. Another says, the state encodes spatial weight in one arm and spin weight in the other, and the probes read those weights. Both honor the data and the rules. They differ on whether to treat properties as co-located features of a tiny object or as context-defined features of a distributed state. This connects back to familiar knots. The measurement problem asks how possibilities become records. Weak probes show how information can be present without forcing a single projective outcome. Wigner's friend raises observer-dependent descriptions. Weak measurements formalize conditioning on later data, which changes what you infer about earlier stages. Entanglement shows non-classical relations across space. The Cheshire Cat shows non-classical relations between where and what within one device. In quantum information terms, the effect hints that features of a state phase, polarization, spin, can be routed and read separately, suggesting schemes where information flows along distinct channels that meet only at post-selection. Proposals exist for sensing and cryptography that exploit this routing. An interceptor who does not capture both channels cannot reconstruct the encoded variable because neither channel alone carries a full classical record. Whether such use is mature depends on noise, loss, and throughput. Weak couplings mean small signals and many trials. Post-selection discards runs, lowering rates. Devices that try to boost speed must balance these costs against the benefit of keeping coherence. For now, the experiments are precise reminders that quantum systems do not match the object property picture of everyday life. The state carries possibilities that can be teased apart by context, then recombined to make ordinary clicks at the exit. A different thought experiment shifts from properties to experience. In the many worlds interpretation, MWI, the quantum state is universal and evolves smoothly at all times. There is no extra collapse. When a measurement happens, the combined state of system, device, and observer branches into components that no longer interfere. Each branch contains definite records. People inside a branch recall one outcome, and every branch follows the same deterministic rule. Quantum suicide, sometimes called quantum immortality, asks what this framework says about survival from the inside. Imagine a quantum randomizer with two equal outcomes. A lethal actuator is triggered by one outcome and does nothing on the other. In MWI, the combined system branches. In some branches, the actuator fires and the observer's history ends. In the others, the actuator stays idle, and the observer's history continues. An outside witness assigns a 50/50 chance for a single trial, 25% survival after 2 trials, and so on. The outside ledger lists a rapidly shrinking fraction of branches with a living participant after many repetitions. Subjective experience cannot continue in branches where the observer dies. The only stream that persists is the stream located in surviving branches. After 1 trial, that stream lies among the safe outcomes. After 2 trials, it lies in the subset where safety occurred twice. Repeating the procedure multiplies branches, but the first-person perspective, by definition, follows only the subset in which experience continues. The phrase quantum immortality labels the conditional statement. Conditioned on continued awareness, the apparent outcome is always survival, no matter how small the branch weight becomes in the outside accounting. This is an extreme application of branching, not a laboratory plan. It rests on strong assumptions that MWI is the correct ontology, that consciousness tracks branch structure straightforwardly, that the lethal coupling can be made perfectly quantum with no classical noise. Real actuators are macroscopic and messy. Isolation fails well before any threshold. Decoherence dumps phase information into the environment. Ethical and legal issues make the scenario purely hypothetical. No scientific program endorses building such a device, and discussing it is not a suggestion to attempt self-harm or any risky test. In foundations, the setup functions as a probe of concepts. MWI ties probabilities to branch weights, while lived experience selects only branches in which experience continues. So, likelihood looks different from inside and outside. The difference sharpens with repeated trials. After an independent 50/50 runs, an outside ledger expects a surviving fraction of 2n. From the first-person view, conditional on being there to notice, the observed record contains only safe outcomes. The tension centers on probability. In standard practice, the Born rule assigns probabilities with squared amplitudes and is checked by frequencies across many runs. In MWI, deriving the Born rule inside a deterministic branching picture is a core task. Approaches use symmetry, invariance, decision theory, or typicality measures over branches. Quantum suicide stresses that a conditional survival-filtered viewpoint considered odds with outside frequencies if survival decides which records can be observed. Identity questions follow. If every allowed outcome occurs, what does I refer to? Many accounts tie identity to continuity of physical processes and memory. Then branching produces multiple successors who each claim to be the original according to their preserved memories. Quantum suicide filters successors by killing those in some branches, leaving only those who remember successive survivals. From the outside, most trials end the line. Inside any continuing branch, the memory chain remains unbroken. Statements like, "I will observe survival," must be read carefully as a measure-weighted prediction across successors before trials, or as a conditional statement about at least one successor afterward. Other interpretations change the framing. Collapse models add stochastic dynamics so that one outcome is selected objectively. Repeated trials just multiply ordinary risks. Hidden variable theories keep definite outcomes guided by a non-local structure. Survival is set by initial hidden conditions, not by branching. Relational and agent-centered views keep probabilities personal to each agent's future experiences. avoiding global claims about what really happens across unobserved alternatives. In all cases, no safe experiment distinguishes interpretations by encouraging dangerous trials. The scenario stays a tool for thinking through how outcomes, probabilities, and observers fit together. Even without many worlds, the setup is a sharp lesson in conditioning. In laboratory analysis, conditioning is explicit when you build coincidence tables or select subsets. The rules are clear. In life and death talk, conditioning hides inside as long as experience continues, which filters the sample and changes apparent probabilities. Making the filter explicit clarifies which claims are empirical and which hinge on perspective. A rational agent following decision theory derivations of the Born rule in MWI would still assign low credence to long survival streaks before any test, because choices are evaluated by branch weights, not by the existence of at least one branch in which a desired outcome occurs. Device considerations matter, even in thought. To qualify as a clean quantum test, the trigger must remain coherent until the final moment, with no uncontrolled leakage that effectively measures the outcome early. Any pre-selection or environmental coupling that reads the random bit upstream collapses the premise into a classical draw. Practical actuators, sensors, and control lines make such idealization untenable. The thought experiment keeps attention on formal points: how amplitudes map to frequencies, how observers enter the same physical description as measured systems, and how language should mark the role of context and conditioning. The broader theme returns. Quantum theory delivers stable recipes for preparation, evolution, and readout, yet it does not fix one story about what those recipes mean. Weak measurements expose structure without forcing a single outcome. Interferometers display property routing that breaks the classical link between object and attribute when probed gently and sorted by post-selection. Entangled games beat classical limits without communication and turn joint statistics into a resource. Branching pictures raise questions about probability and experience that play out differently inside and outside a set of records. The technical statements how to prepare states, which observables to measure, how to compute conditional probabilities remain crisp, and the discussion proceeds by stating those conditions and tracking which claims depend on them. Extend the idea to everyday life. Your body and brain host vast numbers of quantum events each second. Most are harmless background. A few might matter tiny triggers that could start or stop an arrhythmia, nudge a blood clot, flip a molecular switch in a neuron, or allow a DNA repair to succeed. In a many worlds picture, some branches see those micro-events go one way, and others see them go another. In some branches you die, in others you live. The quantum immortality claim follows a simple line. Your conscious stream can only continue in branches where it still exists, so experience always finds itself on a surviving path. From the inside, survival would be the only thing you ever notice, even if, in the outside tally, most versions of you end quickly. At first glance, that seems like a strange kind of comfort. On a second look, it is thinner than it appears. The claim does not promise health, comfort, or normal life. It offers bare survival. The branch you ride could be painful or lonely. You could be the only survivor of an accident, or alive with severe injury, or trapped by illness, with the physiology just barely staying above the line. Nothing in the logic blocks those cases. The picture also says nothing about aging. Biology still wears down. In the imagined long tail, you could occupy branches where rare fluctuations keep key processes running, but leave cognition weak or intermittent. That is not the wish people mean by immortality. There is a deeper worry about the setup itself. It leans on two big assumptions: that many worlds is the right ontology, and that consciousness can be tracked cleanly across branches. We do not have a tested theory of consciousness. We do not know whether awareness splits one for one with quantum branches, or whether attention, memory, and a sense of self require a level of neural coherence that fails in many of the surviving stories the logic imagines. Even physicists who, like many worlds, tend to be skeptical of quantum immortality. They point to measure the weight each branch carries in the squared amplitude sense. After repeated risky events, almost all of the total measure sits in branches where you are gone. In that bookkeeping, you mostly die, even if a thin set of branches still includes a living observer. Identity makes the ground shakier. If the state branches often, then there are many near copies of you, each with a legitimate claim to being you by continuity of memory and structure. On that view, saying, "My experience continues in the surviving branch," singles out one successor among many equally valid ones. A different stance ties you to branch measure rather than mere existence. Then the branch where you beat a long streak of risks counts as almost none of you. Another stance says selfhood is a pattern spread across branches, so singling out one thread is a choice of description rather than a deep fact. None of these options is settled science. They are attempts to make the language of persons match a branching physics. There is also the issue of what it would even mean to experience death. The thought experiment treats death as an end of experience, so there is nothing it is like to be in the dead branch. But someone might argue that the dying process itself is an experience that occurs in some branches. If so, it is not true that experience never includes losing outcomes. It includes them up to the final moment. Another line says that experience requires working brain dynamics that fail in many marginal survival branches. Then the supposed continued awareness would not meet the bar. Both lines push the scenario away from simple slogans. From a physics angle, the idea raises the question of probability in many worlds. In practice, the Born rule gives the frequencies we expect across many runs weights as squared amplitudes, and it works. In many worlds, the state evolves deterministically. Probability is not a dynamical law, but a rule for rational expectation across branches. Derivations try to justify Born weights using symmetry arguments, decision theory, or typicality within large ensembles. Quantum immortality highlights a stress point, a conditional, first-person filter. I only notice branches where I continue does not match the outside measure used for prediction. The fix is not to discard the Born rule, but to be careful about which question is being asked: expected frequencies across branches versus the structure of a single conditional narrative. Device realism matters even in thought experiments. For the suicide machine to be quantum, the trigger must remain coherent until the last instant, with no early leakage that lets the environment read the bit and decohere the system upstream. Real actuators and sensors are messy. They interact with air, wiring, and heat baths. In real gear, outcomes go classical early, long before any lethal gate, and the tidy split assumed by the scenario fails. None of this is a plan for an actual test. It is a way to stress how an interpretation connects formal branching, probability, and experience. Set aside lethal gadgets and ask about ordinary life again. Many worlds would say your world line fans into many near copies every moment. Most of those branches stay close together because most micro-events wash out. A few diverge. Decisions, chance meetings, and rare accidents create paths that look very different. If all branches are real, there is no single privileged thread that owns your name. There is a family of related histories. Quantum immortality presses on what that means from the inside. Is you a single thread that hops between branches that preserve life, or a cloud of threads weighted by measure, or a pattern defined only when someone compares records? These questions do not yield clean lab tests. The scenario cannot be run ethically, and even if it could, its key claim is private. From the outside, survival across many trials looks wildly unlikely. But unlikely things do happen. No observer can tell whether a lucky run is proof of branching or just chance in a single world picture. From the inside, continued awareness carries no flag that says which ontology is true. There is no shared record that could decide the issue, the way a Bell test decides between local realism and quantum predictions. Even so, the thought experiment has value because it forces care with language and assumptions. It shows how a simple shift in perspective from an ensemble view over many branches to a conditioned view inside one can make probability talk slide around. It reminds us that claims about what you will observe must state the conditioning and the measure they use. It also keeps the difference between operational and interpretive statements in view. Operationally, we rely on the Born rule, decoherence theory, and thermodynamics to model devices and brains. Interpretively, we pick a story about what the wave function means and how observers fit into physics. Mixing the two without clear labels creates confusion. The same caution links back to earlier topics. Weak measurements, delayed choice setups, Wigner-style scenarios, and pseudo-telepathy games all carry subtle conditionals. Which data are kept, how they are sorted, which contexts are allowed. Those conditionals do not erase causal order or permit messages to the past. They set which joint patterns appear when records are compared. Quantum immortality moves the conditional into the notion of a self, given that I am still here to notice. Once placed there, probabilities look different, but the move is philosophical, not a new physical effect. In practice, guidance is simple. Use quantum theory to compute device behavior, brain energetics, and noise. Use decoherence to explain why macroscopic records stabilize and why shared facts emerge in ordinary life. Keep interpretation claims labeled as such, especially when they touch identity or survival. Stay clear on measure when making any claim about how likely a long sequence is meant to be, and keep first-person conditionals distinct from ensemble predictions. Where consciousness enters, mark assumptions rather than sliding them in quietly. Extend the idea to daily life. Your body and brain host a huge number of quantum events every second. Most of them average out. A few could matter. A tiny fluctuation might help or hinder a heartbeat. A chemical bond in a neuron could switch one way or another. A DNA repair could succeed or fail. In a many worlds picture, branches exist where these micro-events tip toward harm, and branches where they tip toward safety. In some, you die. In others, you live. The quantum immortality argument says your conscious experience can only continue in branches where it still exists. From the inside, survival is the only outcome you ever witness, even though, in an outside tally, most versions of you end quickly. That promise is thin. It does not say you survive well. It only says you survive. The branch that carries you forward could be painful or lonely. You could outlive others in a disaster. You could live with major injury. You could face illness that leaves awareness dim but still present. Nothing in the logic stops those cases. The idea also says nothing about aging. Cells still wear down. Systems still lose efficiency. If you project far out, you can imagine branches where rare fluctuations keep basic functions going while clarity fades. That is not the kind of immortality people hope for. The setup leans on two heavy assumptions. First, that many worlds is the correct way to read quantum theory. Second, that consciousness can be tracked cleanly across branches. We do not have a tested theory that tells us how awareness maps onto branching physics. We do not know whether a mind splits one for one with each branch, or whether attention and memory need a level of neural coherence that fails in many of the marginal survival paths the story imagines. Even physicists who favor many worlds tend to doubt quantum immortality. They point to branch measure, the weight linked to squared amplitudes. After many risky events, almost all of the total measure sits in branches where you are gone. In that bookkeeping, you mostly die, even if a thin set of branches still includes a living observer. Questions about identity go deeper. If the quantum state branches often, there are many near copies of you, each with a clean claim to continuity by memory and structure. On that view, saying, "My experience continues in the surviving branch," singles out one successor among many equally valid ones. A different stance ties you to measure rather than mere existence. Then a branch with an unlikely survival streak counts as almost none of you. Another stance treats the self as a pattern spread across branches. There is no single thread that owns your name. These are not settled facts. They are attempts to make language about persons fit a branching physics. There is also the question of what it would mean to experience death. The thought experiment treats death as an end of experience. In that frame, there is nothing it is like to be in a dead branch. Someone could reply that the process of dying is still experience in some branches up to the final moment. So loss does appear in lived time. Another reply says that experience needs a level of brain function that is absent in many surviving branches where physiology is badly damaged. Both replies push the scenario away from simple slogans. From physics, the issue becomes a question about probability. In practice, the Born rule matches frequencies in long runs. In many worlds, the state evolves without collapse. Probability is not a new force, but a rule for rational expectation across branches. Projects to justify that rule in MWI use symmetry, decision theory, or typicality. The quantum immortality story stresses a gap, a first-person filter. I only notice branches where I continue does not match the outside measure used for prediction. The way to keep things straight is to mark which question you are asking. One question is about expected frequencies across many branches. Another is about the structure of a single, conditioned narrative that exists only where awareness persists. Even as a thought experiment, the device model matters. For a quantum suicide machine to match its premise, the trigger must remain coherent until the last instant. There must be no early leakage that lets the environment read the random bit and decohere it upstream. Real actuators and sensors are macroscopic and noisy. They couple to heat baths, wiring, and air. In real hardware, outcomes become effectively classical long before any lethal gate fires, and the tidy split assumed by the scenario fails. The setup is not a lab plan. It is a probe of how an interpretation links formal branching, probability, and experience. Shift back to ordinary life. Many worlds would say your history fans into many near copies at every moment. Most branches stay close because most micro-events average out. A few diverge in visible ways. A decision, a meeting, a near miss on the road, a rare illness path split. If all branches are real, there is no privileged thread. There is a family of related histories. Quantum immortality pushes on what that means from the inside. Is you a single line that always follows survival, a cloud of lines weighted by measure, or a pattern only defined when records are compared? The idea is not a test in the usual sense. It cannot be run ethically. It would not resolve anything even if it could. From outside, a long survival streak is wildly unlikely but not impossible in a single world picture, so it does not decide between views. From inside, continued awareness brings no label that says which ontology is true. There is no shared record that could settle the question the way a Bell test settles local realism. Still, the thought experiment is useful as a check on language. It shows how conditioning changes probability talk. In lab work, conditioning is explicit when you build coincidence tables or select subsets. In this story, the conditional sits inside the phrase, "as long as I am here," which filters the sample and shifts what seems likely. Being clear about the filter helps keep claims in scope. There are practical edges to note. Brain function runs on classical-looking scales, but the components are quantum at base. Decoherence explains why neural states stabilize quickly and why shared facts about the world emerge. It also warns that most branch splits, relevant to brain-level patterns, are soaked by the environment and never form tidy, coherent alternatives that persist. The picture of precise, isolated splits, steering life or death outcomes on demand, is not how complex biology works. Even if rare micro-events sometimes tip a system, most macroscopic outcomes flow from robust, high-entropy processes shaped by physiology and environment. A narrower claim survives all of these caveats. If many worlds is right at a fundamental level, then versions of you exist in many branches, most of them nearly alike, some not. In branches where high-risk events recur, the outside measure of ongoing versions drops fast. A first-person narrative that conditions on continued awareness will always be carried by the rare streaks that happen to survive. That is a statement about how conditionals behave, not proof of a safe path through danger. The thought experiment also marks where physics hands off to other fields. Questions about identity, continuity, and what counts as an experience touch philosophy of mind and cognitive science. Questions about decision and expectation touch probability theory and rational choice. Questions about device isolation and decoherence are engineering and physics. Mixing these domains without labels makes strong claims sound definitive when they are not. A practical reading comes out of this. Use quantum theory to model devices and biological processes where it applies. Use decoherence to explain why everyday records are stable and shared. Keep interpretation statements marked as such, especially when they touch survival or self. Keep branch measure visible whenever you talk about how likely a long run is meant to be. Keep first-person conditionals distinct from ensemble predictions. Where consciousness enters the story, state your assumptions rather than letting them hide inside the wording. One family of ideas roots the puzzle through information. The holographic principle says a region's full content can be encoded on its boundary. like a flat hologram that holds all the data for a 3D image. For black holes, the event horizon acts as an information surface. Tiny patches of area count bits. When matter falls in, new bits appear on the horizon. As Hawking radiation leaks out, information must leave with it. This picture links gravity, thermodynamics, and quantum theory. In some string theory models, a universe with gravity is exactly equivalent to a quantum system on a lower dimensional boundary with no gravity. That does not make space fake. It suggests space-time may emerge from more basic quantum data. What remains unclear is the mechanism. How is the fine pattern on the horizon written, scrambled, and then released? Which degrees of freedom store it? How can a falling observer see smooth space while a distant observer later recovers detailed information from faint radiation? The math supports unitary evolution, but a step-by-step map from infall to outgoing quanta is not settled. This set the stage for the firewall paradox. The firewall argument starts from three claims most physicists want to keep. Quantum evolution preserves information. Physics outside the hole looks local and causal, and a freely falling observer feels nothing special at the horizon. In 2012, the AMPS group showed that all three cannot hold together if Hawking radiation carries out information. To imprint the right correlations in the radiation, the entanglement that normally smooths the horizon would have to break. The price is a band of ultra-energetic quanta at the horizon, a firewall that would burn anything crossing it, clashing with the equivalence principle. Responses differ on which claim to relax. Some adjust assumptions about how entanglement is shared between early and late radiation, allowing state-dependent rules or subtle non-local ties that keep the horizon calm for infallers. Others accept that horizon structure might emerge in late stages, but seek a gentler description that does not violate every test of relativity. A few keep the firewall idea, but try to limit when and how it appears. Each option preserves quantum consistency by bending classical expectations in a different place. These debates live inside the larger search for quantum gravity. String theory gives a precise holographic duality, add divided by CFT, where a gravity theory in a volume equals a quantum field theory on its boundary. In that setting, information is manifestly preserved. It also reproduces black hole entropy by counting microstates in special cases. Loop quantum gravity quantizes geometry itself, suggesting areas and volumes come in discrete units, which could alter what horizon means at the smallest scales. Other lines build geometry from entanglement networks, so that changing correlation patterns reshape space. In those pictures, information flow and space-time structure are two sides of the same coin. Direct black hole experiments are out of reach, but analogs help. Fluid flows can create sonic horizons, and optical systems can mimic horizon effects. These models do not solve gravity, but let us test how horizons mix modes and how thermal-like emission can arise. On the theory side, quantum field theory in curved space-time shows how Hawking quanta come from mode mixing, and how subtle, long-range correlations could hide inside emission that looks thermal at first glance. Over time, the view is shifted. Early readings treated Hawking radiation as perfectly thermal, with no fine detail. Newer work points to tiny deviations and long-range correlations that could carry information. Scrambling theory suggests black holes mix inputs quickly, then release them slowly in a form that is, in principle, recoverable if one has the entire record. Holographic tools let researchers track when information begins to come out, the page time, and how entanglement between the hole and the radiation evolves. Calculations using quantum extremal surfaces indicate that late-time radiation can encode interior data in a unitary, consistent way in certain setups. Tension remains. If the horizon stores and releases information, what does a falling astronaut measure locally? If interior data can be reconstructed from complete radiation, how is that compatible with an interior that looks real to someone inside? If the fix involves non-locality, how is it limited so signals never outrun light? If it involves state-dependent observables, how do we keep predictions objective and reproducible? Patching one seam often pulls on another. Quantum information language helps. Holography behaves like a quantum error-correcting code. Bulk information is redundantly encoded on the boundary. Enough boundary pieces allow recovery. Too few reveal nothing. This explains how interior data might be reconstructible from Hawking radiation plus what remains of the whole, at least in ideal models, and why partial access gives no usable signal. The code picture reframes the question, not where did information go, but which boundary degrees of freedom and which decoding make it accessible. Some researchers push beyond current frameworks. Maybe space-time and quantum states are two descriptions of one underlying combinatorial structure. Maybe time is emergent, and a single, global causal order across all viewpoints is too strict. Maybe gravity slightly modifies quantum rules in extreme regimes, changing how entanglement can be shared. Such proposals need to match known physics and suggest tests before they move from sketches to theories. Because direct data are scarce, consistency is a strong guide. Any solution must fit precision tests of general relativity in weak fields and precision tests of quantum mechanics in the lab. It must respect thermodynamics, including the generalized second law that counts horizon area as entropy. It must obey no signaling. It should explain why semi-classical gravity works so well almost everywhere, while breaking down in the right, narrow places. Black holes are ideal probes because they demand both theories at once and make mismatches visible. Even without a final map, pieces are already useful. Holographic dualities act like wind tunnels for ideas. Error correction models give a language for how geometry stores data. Scrambling sets timescales for mixing information. Firewall-style thought experiments force careful accounting of entanglement. Analog horizons refine how we talk about modes and observers. Quantum extremal surface calculations give concrete handles on when and how information can emerge in models that remain unitary. All of this loops back to measurement and context. Hawking's original calculation used the local vacuum near the horizon in a freely falling frame, then related those modes to distant detectors and found a thermal flux. Later work asks for the full state that includes the collapsing matter, near horizon modes, and far-field quanta. The answer looks like a highly entangled global state that appears thermal in small pieces but is structured in the whole. That pattern, local randomness, global order revealed by the right correlations, matches what quantum theory predicts in many settings. What an outside observer can reconstruct from radiation depends on access to long records and on the decoding used. What a falling observer perceives depends on local instruments and short timescales. Demanding a single, simple description that ignores which observables are available to which observer is what breeds paradox. Keeping track of the measured subsystems, the partitions used in entropy calculations, and the entanglement cuts that define inside versus outside keeps the accounting within tested rules. Calculations then depend explicitly on those choices of observables and partitions, rather than on a single, all-purpose picture. In classical physics, a measurement is a clean readout. An object carries definite properties. A device couples to those properties and reports them. If the device is gentle, it barely disturbs the object. It just reveals what was already there. Quantum theory changes each part of that script. Before a measurement, a system is described by a wave function that assigns probability amplitudes to many possibilities at once. An electron is not at A or at B. It has a spread of chances tied to A and to B. When a detector clicks, one result appears. We describe that abrupt change as collapse. A broad superposition narrows to a single outcome. Between measurements, the wave function evolves smoothly under the Schrödinger equation. That evolution is deterministic and reversible. Knowing the state now lets you predict the state later. During measurement, the textbook rule switches. Outcomes are selected randomly, with chances given by the Born rule, and alternative possibilities are discarded. Two rules, two kinds of change. The hard question is when and why the rule switches. What counts as a measurement if everything, including detectors, is made of quantum parts? Write the detector into the quantum description and, in principle, the combined system should still evolve smoothly. Yet in practice, we never see a screen half lit and half dark as a stable superposition. We record definite numbers and pointer positions. The tension is the measurement problem. Quantum mechanics gives one evolution for isolated systems and another for observed systems without a crisp, universally accepted criterion for the boundary. A key piece of the practical story is decoherence. Real detectors touch vast environments: air, photons, vibrations, electronics. Those countless interactions entangle the device with its surroundings and rapidly suppress interference between different macroscopic outcomes. In effect, the environment measures the device, selecting robust pointer states that spread as redundant records. Decoherence explains why superpositions of macroscopically different detector readings are not seen. Their delicate phase relations leak into the environment and become unrecoverable. Decoherence does not, by itself, select one outcome. It shows why mixtures behave classically and why different outcomes cease to interfere. It tells us why classical-looking records are stable. It does not tell us why one record is realized rather than another. Interpretations answer that last step in different ways. The Copenhagen family treats the wave function as a tool for calculating probabilities. A measurement is when we use a classical description to register an outcome. Collapse is an update to our knowledge after gaining information. Copenhagen is practical and matches lab work, but keeps the cut between quantum system and classical apparatus somewhat flexible. It does not claim a hidden mechanism. It fences off the question and focuses on prediction. Everett's many worlds removes collapse entirely. The universal wave function always obeys the Schrödinger equation. A measurement is just entanglement between system, device, and observer. Decoherence splits the global state into branches that no longer interfere, each with a consistent record. You experience one branch because you are part of that branch. The Born rule must then be justified inside a branching world, often via symmetry, invariance, decision theory, or typicality. The payoff is one rule for all processes. The cost is a vast multiplicity of coexisting outcomes. Pilot wave mechanics restores definite particle positions guided by a quantum wave. The wave obeys the usual equation and steers trajectories through a non-local guidance law. Outcomes are fixed by initial conditions. Collapse is only effective, not fundamental. The theory is deterministic and realistic about positions, but the guidance is explicitly non-local, and the wave itself is not directly observable. Relational quantum mechanics says state assignments are always relative to an observer or system. A result is a fact for the observer who registered it. There is no observer-independent, absolute state of the entire world. When observers compare notes, their records align through interaction. Until then, different descriptions can coexist without contradiction. Collapse is a change in relational information, not a physical jump. Objective collapse models like GRW and CSL add new dynamics to standard quantum theory. Superpositions of large or massive systems spontaneously localize at random times, with rates set by new constants. Microscopic systems almost never collapse. Macroscopic superpositions collapse quickly. These models make testable predictions, tiny deviations from standard quantum noise and energy spectra, and experiments seek or bound such effects. Quantum Bayesian, cubist, and related psi-epistemic views interpret the wave function as an agent's personal betting odds for future experiences. Collapse is updating those odds upon learning an outcome. The theory becomes a normative rule for consistent beliefs constrained by the quantum structure, not a literal map of a wave moving in space. The focus is on how agents should assign probabilities, not on hidden processes. Consciousness-based ideas place the cut at awareness, suggesting that mental observation completes measurement. Most physicists avoid this route because it drags ill-defined concepts into physics and raises questions that are hard to test. If minds cause collapse, which minds, and by what physical channel? Each path trades one kind of clarity for another. Copenhagen is modest about ontology and strong on use. Many worlds is clean on dynamics and heavy on ontology. Pilot Wave is clear on particle reality and non-local by design. Relational and cubist views are clear about information and cautious about view from nowhere claims. Objective collapse is clear about when superpositions end and must face experimental bounds on new noise. None alters the successful predictions in ordinary experiments. They reorganize the story about what is real and why outcomes are definite. Ideas from quantum information help organize the terrain. Decoherence and quantum Darwinism show how environments broadcast records of certain stable properties, making them classical-looking for many observers at once. Error correction language suggests that macroscopic records can be redundantly encoded and robust against small disturbances. Context and accessibility matter. Which observables are measured, which subsystems are accessible, and which cuts define system, apparatus, and environment. Many paradoxes soften when those choices are spelled out. Operationally, laboratories do not wait for consensus. They prepare states, evolve them, couple them to detectors, and analyze statistics with the Born rule. Decoherence theory guides how to protect fragile quantum information and how to design readout that is fast and reliable. Loophole-free tests confirm that no local, non-contextual hidden variable model can underwrite the numbers. Device-independent protocols lean on violations of classical bounds to certify randomness and security without peeking inside hardware. Across all of this, measurement is a controlled interaction that produces a stable, readable record. What remains is the conceptual gap. One set of rules for smooth evolution, one for outcome selection, and a gray area about when the switch occurs, or a promise that no switch occurs. and branching explains appearances, or a claim that switch is just an update of information relative to an observer. The gap matters because it touches what we count as a fact, how we think about cause and effect, and how we place observers within the same physics as the systems they study. The practical tools are firm. Write the Hamiltonian, model the couplings, include decoherence, and compute the statistics that readout devices will show. The interpretive choices guide the stories we tell about those statistics and about the world they describe between one click and the next.